Hello everyone, my name is Simran and today I'll be presenting our work titled Early Prediction and Clinical Decision Support for Septic Shock in Intensive Care Unit Patients Using Relational Reasoning with Large Language Models. Sepsis and septic shock are medical emergencies where every hour of delay in diagnosis can significantly worsen patient outcomes. One of the biggest challenges is that early symptoms are often vague and overlap with many other critical illnesses, making diagnosis difficult for both clinicians and artificial intelligence systems. While many existing AI models can predict sepsis with good accuracy, they often function as black boxes. They provide a prediction but not the clinical reasoning behind it, and they struggle to distinguish sepsis from other conditions with similar presentations. This can lead to false inferences and reduce clinician trust. Our research addresses this gap by developing a clinically grounded framework that combines machine learning with large language models to support both early septic shock prediction and differential diagnosis. Before designing our framework, we asked a simple question: can a large language model accurately interpret raw patient data on its own? Our preliminary studies compared different prompting strategies, including zero-shot and few-shot prompting. What we found was that large language models could not reliably interpret continuous clinical values without additional clinical context. In other words, numbers were not enough. They needed medical reasoning to make meaningful decisions. To develop and evaluate our framework, we used several large ICU datasets containing real patient information, including vital signs, laboratory values, and other clinical measurements collected throughout patients' hospital stays. The framework we developed is called Arisen Shock, which stands for Agent-Based Recursive Interpretable Sepsis Early Warning Network for Septic Shock. Rather than relying on a single AI model, we divided the clinical reasoning process among three specialized AI agents. The first agent summarizes the patient's clinical data and identifies important patterns. The second serves as a medical knowledge expert, establishing clinical guidelines and diagnostic criteria. The third focuses on differential diagnosis by considering other conditions that may resemble septic shock. Finally, these agents report to a recursive coordinator, which gathers evidence from each perspective before reaching a final conclusion. This collaborative reasoning process helps reduce bias and prevents the system from making premature or unsupported predictions. For Agent A, we analyzed more than 40 clinical variables across multiple ICU datasets to determine which patient features were most informative. Using feature importance analysis, we identified key predictors such as temperature, respiratory rate, heart rate, and oxygen saturation. We then evaluated several machine learning models. Our results show that XGBoost achieved the strongest performance, outperforming both the published baseline model and Random Forest. One of the most important findings from this stage was recognizing that machine learning is better suited for making predictions, while large language models are far more valuable for explaining those predictions in clinically meaningful language. The second component of our framework grounds the system in established medical knowledge. Rather than allowing the large language model to reason freely, we provided it with accepted clinical definitions, diagnostic guidelines, and evidence-based thresholds for important physiological variables. This ensures that its explanations remain medically accurate and clinically interpretable. The third agent strengthens diagnostic reasoning by considering conditions that commonly mimic septic shock, including cardiogenic shock, hypovolemic shock, and diabetic ketoacidosis. Instead of simply predicting septic shock, the framework actively evaluates alternative diagnoses before reaching a conclusion, helping reduce diagnostic errors. Finally, the recursive coordinator brings everything together. It continuously gathers evidence from each specialized agent, compares their reasonings, and builds an evidence-based conclusion supported by patient data, medical guidelines, and differential diagnosis. Overall, our work establishes an interpretable, clinically grounded framework for early septic shock prediction that combines the strengths of machine learning and large language models. Thank you very much for listening.